So yeah, this is acids and bases, part I don't know, I think 6, no 7 maybe. Where the last couple of times we've been talking about something called a buffer. The buffers are things which can control the pH by being mixtures of weak acids or bases, and then either their conjugate base or acid. And the power of these things is based on their ability to react with excess acid or base that is added because they themselves contain the components to react with that. So for example, in the buffers, if we added an acid, the base that is within the buffer system would react with it to kind of neutralize it, and then that would reduce the effect of the pH change. Now, buffers exist in a lot of different places. They're very important in biological systems. They're very important in certain cosmetics as well, pharmaceuticals and things like that, to make sure that the product that we make in the factory or whatever is going to be consistent with the product which the consumer uses at the end use case. Now, we will encounter buffers again later on whenever we talk about a way of quantitatively determining how much acid or base is in a solution through a titration. There will be buffers involved there. But first of all, I want to sort of do a quick recap of the last topic we talked about last time, which was a determination of a particular principal species. So this is the idea of, if I know the pKa of an acid, and then I know what pH I'm working with, hopefully I should know what form the acid is in, or if it happens to be a base, what form the base is in. This is solely based on the comparison of the two numbers. It's not really involving a huge amount of calculation, really just a comparison of the two values. So whenever we had the Henderson-Hasselblatch equation, we had it here. So hopefully we recall this, where the pH is equal to the pKa plus or minus the log of the concentration of the conjugate base over the conjugate acid. And so this was typically used for a buffer system. Remember that we can have our acid dissociation reactions of HA dissociates in water, of course. Don't forget, this is mostly aqueous solution that we talk about because it's the simplest, giving H plus plus A minus. So the A minus is going to be the conjugate base of HA, but A minus comes from a salt, remember, in a buffer. It doesn't come from HA. So HA is a weak acid, but anyway, this equilibrium exists, and so A minus and HA come from the same kind of species. So A minus is from the salt. This is the weak acid that we add. So basically, the pH is going to be dependent on the pKa value for whatever it happens to be. In this case, benzoic acid 4.20, plus or minus the ratio between the conjugate base and the conjugate acid. And so depending on the value of this ratio, it will change what is added or subtracted from our pKa value. So in this case, for the benzoic acid, it's going to be pKa is equal to 4.2, obviously. So it's going to be 4.2 plus or minus one or other of these, whatever it happens to be. So whenever the concentrations are equal to each other, so for example, if the concentration of A minus is 1 mole per liter and the concentration of HA is 1 mole per liter, that would give a value of 1 over 1, which is 1. So log of that would mean that log of 1 basically is 0. So we end up having a value of 4.20. So whenever we have a situation where the concentrations of the conjugate base and the weak acid are the same, the pH will be 4.2. Whenever the concentration of the weak acid is larger than that of the conjugate base, we have a pH which is going to be less than 4.2, because this number is going to be larger than this number. So this number is going to be kind of small, which means that it's going to be subtracted from this number, which means the pH will get lower. And then conversely, if we have a larger amount of this and a smaller amount of this, so for example, 2 over 1 or 3 over 1 or something like that, then the pH will increase because the amount of conjugate base is larger than that of conjugate acid. So if we have a situation wherein we have pKa of benzoic acid of this, the pH of 8, it means that the pH is now higher than the pKa value. So usually if the pH is going to be larger than the pKa value, that means we're going to have more conjugate base than conjugate or weak acid, which means that we will end up having a predominant species of A- in our solution. So an acidic realm would mean we have predominantly HA. A basic realm would mean we have predominantly A- based on our center point of 4.2 based on our pKa. Now, this is only the pKa for benzoic acid. If it was a different acid we're dealing with, we would have a different value of pKa, and that would set our midpoint somewhere else. So at this point, pKa is equal to 4.20. We have equal concentrations of HA and A-. That's why I'm calling it the midpoint. Then if we have more A-, the pH increases, and so we have a more basic system. And then if we have more HA than A-, then we have an acidic system, and our pH is going to be somewhat acidic. So at pH 8.0, the base form A- predominates because the pH is greater than the pKa, which means that A- is going to be greater than HA. Now, this doesn't just come out of nowhere. It comes from the Henderson-Hasselblatch equation. You can like put values in here, like any random values you want. Just make sure that in one case they're the same, in one case they're different, where A- is larger than HA, and in one case HA is larger than A-. And you can see that this kind of phenomena plays out. So then some calculations based on this. This is all from the previous session. I just wanted to go over it again. So what is the predominant form of NH3 at pH 7, and how much of it is there? So the pKa of the ammonium ion, so this NH4 plus ammonium, is equal to 9.24. And this means that at pH 9.24, the concentration of the ammonium is equal to the concentration of ammonia. So since pH 7 is about 2 pH units below 9.24, the predominant form will be the acid form, the NH4 plus. So pH 7 is about 2 pH units below pKa, and so the quotient of NH4 plus over NH3 will be about 100 to 1, or 99%. So why is it this? Well, it's because of the way that logs work. So logs are based on the number of really log of the base 10 is really just counting how many zeros there are. So if it's going to be, if the value of, let's see, so the value of our pH is 7, which is about 2 units below that. So that means that log to the base 10 of whatever the quotient is between these is going to be equal to 2, or -2 in this case. And so that means that we will have a ratio of about 100 to 1 between the two species. And so basically the whole thing is going to be ammonium. It's just really mathematics at that point. So what is the principal form of alanine? Alanine is our amino acid. Remember, amino acids have 2 pKa's. They have one for the amine group, and they have one for the carboxyl group. And so we're asked, what is the principal form of alanine? The pKa's are given as 2.34, which would be for the carboxylic acid part, and 9.87, which would be for the amino part at pH 8. So we can set up our diprotic system here, where we have HA, the alanine, and the amphiprotic form in the middle. We have here the conjugate base, and we have here the conjugate acid of the amphiprotic form. So this is going to be in high acid realms. So the this is the fully protonated form. So that means even the carboxylic acid group has a hydrogen attached to it. And in this form here, we have the hydrogens removed from both the carboxylic acid and the amine group. So that means that we have a basic realm here. We have an acidic realm here. Our two regions, or three regions, are separated by 2 midpoints. One midpoint here, 2.34, which is between the fully protonated and the amphiprotic form, and the second midpoint here between the amphiprotic form and the fully basic form. And so these two pKa values are given here. We're told the pH is 8. So if at this point we have equal amounts of this and this, that means we would have a pH of about 8. And here, if we have equal concentrations of HA and A-, we would have a pH of 9.87. We have a pH of 8, which is somewhere around about here. So it's on the amphiprotic point. It's somewhere quite close to A minus, a lot closer to A minus than it is to H2A plus, but we're most likely going to have the amphiprotic form as our predominant species. So the principal form of alanine at pH 8 is the amphiprotic form HA. Okay, so it's just a quick revision of those before we jump into something called fractional compositions, where we can derive equations that give fraction of each species of acid or base at a given pH. So this is based on that sort of like based on the previous slide we had here. This principal species is going to be HA, but it's not totally going to be HA. Some of it is still going to be A minus. So with fractional compositions, we want to know what percentage of all of this is going to be one of these species. So what percentage is going to be the base? What percentage is going to be the acid? For monoprotic systems, the fraction is a little bit simpler. So it's going to be the fraction of HA is equal to the concentration of HA over the formal concentration, which is the total concentration, which is equal to H plus over H plus plus Ka. Ka is our acid dissociation constant. H plus is the amount of HA which has dissociated. So remember, way back, we did something called a reaction table where we could get the concentrations of H plus and things like that for a system at equilibrium. Well, this is going to be something similar where we're dealing again with equilibriums. This is why the equilibrium part of our course was so important, because basically everything that we've done so far in acids and bases is based on that in some way or another. H plus concentration then over H plus plus Ka. Then we have the fraction, which is A minus. So that's going to be equal to the concentration of A minus over the formal concentration. So the total concentration for the system is equal to Ka over H plus plus Ka. So we're asked for an example. So what fraction of benzoic acid exists as benzoate at pH 8.0? So this was going back to the first example that we did earlier, where we were asked the principal species that was present in our solution. So we use the equation there. So we want to know, we're asked not how much benzoic acid there is, we're asked how much benzoate there is. So the fractional composition A minus is equal to the concentration of A minus over the concentration, the formal concentration, which is equal to Ka over H plus plus Ka. So Ka values were given to us as pKa values earlier. The pKa of benzoic acid was told to us to be 4.2. So we want to fill in these values. So we know pH 8. So that means if we remember that our pH is equal to minus log to the base 10 of the hydronium ion concentration or H plus concentration. We rearrange this so that the H plus concentration, that's where the values here come from, is equal to 10 to the power of minus pH. This is just rearranging your logs from your mathematics courses. So you go. So that's the H plus concentration will be equal to 10 to the minus pH. So since we're given the pH value, we can fill this in here. So it's 10 to the minus 8.0 because pH is 8.0 plus the Ka value. So the Ka value, since we know pKa is 4.20, the Ka value then is going to be 10 to the minus 4.20. Again, it's really the similar process. It's just like pKa is equal to minus log 10 of the Ka. So just rearrange that, and then you get Ka as being equal to 10 to the minus pKa. So fill in those values, and then you'll get an answer here, which gives us a value of 0.999 as the fraction of 1 that is benzoate. So that's almost totally benzoate. There's almost no benzoic acid still in solution. And that kind of makes sense because remember what we talked about earlier where the principal species at 4.2, we have, pH 4.2, which is the pKa. We have an equal concentration of the acid, the benzoic acid, and the benzoate. But if we're going to go like really, really far into the benzoate, into the basic part, so we go to like pH 8.0, then what we're going to end up with is something which is predominantly A minus, and that has been revealed to us as the fraction has been almost 1 for the fraction of benzoic acid, which exists as benzoate at pH 8, because we're really quite far away from the original sort of pKa pH. So at pH 8, almost all of the benzoic acid exists in the basic form. And so you can see this graphically here. So we're looking at a monoprotic acid-base system. So remember, HA is equal to H plus plus A minus with a pKa of 5. So remember that the pKa value is going to be correspond to the pH at which we will have equal concentrations of both the weak acid and its conjugate base, or really any monoprotic acid and its conjugate base. So at the pKa, concentration of conjugate base and acid are the same. And any deviation from that changes the ratio of the concentrations. So if we have a pH less than the pKa, we're going to be on the acid side. And if we have a pH larger than the pKa, we're going to be on the basic side. And so we can see that in this graph here. So in this system where HA dissociates to give A minus, we're going to have a pKa of 5. So at 5, we have 50% or 0.5 as a fraction of our system be HA and 0.5 of our system be A minus, which means that we have 0.5 plus 0.5 gives us a total of 1 at the pKa value of 5. So if we then, for example, reduce the pH to 4, so it would be here and here, something like that, we would see that, so about here, about so if we reduce the pH to 4, we can see that there is 0.1 as the fraction of A minus and about 0.9 as the fraction of HA. My line isn't terribly straight, but hopefully you get the idea of what I did. And so you can see that below the pKa, we have a more acid-dominated system. Then if we increase the pH beyond the pKa, then we get the opposite side. So we see that we have, so at pH 6, we have about 0.1 as our fraction of HA and about 0.9 as our fraction of A minus. And so that in a system where the pH is larger than the pKa, the basic form will dominate. And that kind of makes sense if you think about it. So if, for example, I have a system where more base has been added, then my acid needs to dissociate more to sort of neutralize the base. So base is in a pinch, let's say the base is hydroxide. So if we have excess hydroxide, I'm going to need to dissociate more of my acid to react with that base in order to neutralize it. And so more HA continually becomes A minus as the H's are dissociated to react with the OH minus. So it's basically just our neutralization reaction. So excess base means we need more protons, which means we need more dissociation, which means we have less HA. So here is the fractional composition diagram of a monoprotic system with pKa is equal to 5.0. Below pH 5, HA is the dominant form, whereas above pH 5, A minus dominates. Okay. So fractional composition then for diprotic systems. So this is going back to things like our amino acids and also things like our sulfuric acid and things like that. So a little bit more complicated because we now have, remember, two Ka values. We have Ka of the first deprotonation and Ka of the second deprotonation. So the fraction which exists as our fully protonated system is going to be equal to the concentration of the undissociated diprotic acid over the formal concentration, which is just the total of the whole system, which is going to be equal to H plus concentration squared over H plus concentration squared plus H plus plus Ka1 plus Ka1 times Ka2. Hopefully you can see this is actually just a quadratic equation. We have like X squared plus, well, in this case, it's X B. X is the H plus concentration plus C. Even though they're multiplied together, they're basically just in the form of a quadratic equation. Then do the same thing for the fraction of HA minus. So this is the singly deprotonated form. So it's going to be the concentration of HA minus over the formula concentration, which is going to be equal to Ka1 times H plus concentration over the same thing. The total concentration doesn't change. So it's still just x squared plus xb plus c. So it's h squared, or h plus concentration squared plus h plus concentration times Ka1 plus Ka1 times Ka2. And so then the final one then for the fully deprotonated system, we're going to have the fraction of A2 minus is equal to the concentration of A2 minus over F, which is equal to Ka1 times Ka2 over H plus concentration squared plus H plus concentration times Ka1 plus Ka1 times Ka2. If you want to see the derivation of these, it'll be in your textbook, but we don't really have time to go through it. Fractional composition. Okay, so this is a graphical form of what I was just talking about. So it's really quite similar to the previous one. Only the thing is we have one in the middle, which is our amphiprotic system. So this is our singly deprotonated amino acid, something like that. So what happens here is that this part in the middle, this HA minus, this amphiprotic form, can of course gain a proton and go to the acidic region, or release a proton and go to the basic region. But during the center point, like for example, halfway between the pKa's of pK1 and pK2, we have a point where we have all three species present. So for example, here at the peak, which would be around about what, 3.75, something like that, we have present in our solution HA minus, H2A, and A2 minus. So they're all present at this point. It's only really in the very basic or the very acidic regions that we have one or the other in this instance. So for example, at pH 1, we even still have a very small fraction of HA minus, but we don't have any A2 minus. A2 minus is this curve, and at like around about pH 2, there's no more of the A2 minus, but there is still a reasonable amount of HA minus present, but the predominant species is, as we would expect, H2A. The pKs work in a similar fashion for determining the predominant species. So the pKa for the first deprotonation, so H2A going to HA minus, is here. So that's pK1. That's a value of 3.02. So below the pH of 3.02, we would have a predominantly acid system. Above it, we would have the amphiprotic concentration larger than the either the A2 minus or the H2A. Then on the other side, we have the pKa2, which has a value of 4.48. So above this 4.48, any pH is larger than that, say, for example, 6, we have clearly the predominant species is the A2 minus. Then if we look, we still have some of the amphiprotic form, the HA minus, but we end up with effectively no H2A. And this is because most of the H2A has been converted either to HA minus if there's still going to be some protonated forms, or to A2 minus. But basically what we see is that there's really a lot of variation between what is possible, because what ends up happening is that there's no real push towards this being totally deprotonated or this being the predominant species around about the midpoint, because both of them can exist. So for example, instead of having HA minus, I could somehow have H2A and an A2 minus. So instead of having two of these, I could have one of these and one of these, and I would have the same number of protons dissociated in solution. So all of these things exist as a dynamic equilibrium. They're continuously forming and dissociating. And so what ends up happening is that we end up with a jumble of different possibilities, unless, of course, we are in the very basic or the very acidic regions, in which place we have a much clearer picture of what the composition would be. So there's a special sort of term for these things where we have something called the isoelectronic and the isoionic pH, which we will get into definitions of in a moment. But basically, we have these systems which exist. For example, our amino acids, which we've talked about quite a lot, where we have an equilibrium which goes the whole way from the fully protonated form, like this alanine cation, where we have the H plus, or sorry, both the carboxyl and also the what do you call this? The amino groups, both of which have been fully protonated, and that's in equilibrium with the neutral zwitterion, which contains both a negative charge and a positive charge on the same molecule. So even though this molecule is, or this ion, sorry, is charged, it is formally neutral because it contains one positive charge and one negative charge, which sort of like will how do I say that? Which will neutralize each other, plus the proton, obviously, which has been dissociated from the carboxyl acid group. So this is as this pH or pKa. Then the same thing can happen is that the alanine cation or anion, which is also the zwitterion here, can dissociate further to give the conjugate base plus H plus. So these two species here are the same, but they can either be known as a neutral zwitterion or an alanine anion, because they have the ability to, or sorry, this is the alanine anion. They have the ability to dissociate. So the isoelectric and isoionic pHs. So the isoionic pH point or the isoionic pH is going to be the pH obtained when the pure neutral polyprotic acid, HA, the neutral zwitterion, is dissolved in water. So we have only got the ions H2A plus, A minus, H plus, and OH minus. So we have kind of an almost neutral system there, where we have sort of like complementary ions which will neutralize the different charges. So most alanine is in the form HA, and the concentrations of H2A plus and A minus are not equal to each other. So the neutral alanine HA dissolved in water, the pH will be somewhere between 2.234 and 9.87. The A minus concentration will be slightly larger than the H2A plus concentration, and this is the isoionic pH. So H3O plus is equal to, concentration is equal to this equation, which we saw before, where we have to relate our two Ka values to each other, plus the concentration and Kw, of course, Kw being 1 times 10 to the minus 14. So A minus is slightly larger. The concentration of A minus is slightly larger than the concentration of H2A plus, because, pardon me, water is always slightly acidic because of dissolved carbon dioxide. So unless you have totally degassed water and you're holding the water in an oxygen or air-free environment, you're going to have some CO2 dissolved in it. It happens almost instantaneously. And that will cause a reduction in the pH. So a reduction in the pH means it's more acidic, which means that we would end up having a slightly larger A minus concentration. So the isoelectric point then, so the isoelectric point or the isoelectric pH is the pH at which the average charge of the polyprotic acid is 0. So that means, it doesn't mean that we don't have anions and cations present. It just means that the charges given by the number of cations and the charges given by the number of anions is going to be equal. So for example, say I have 2 cations and 2 anions in my solution. That means that the average charge of that would be 0, because I would have 2 out of 4 which would have a charge of +1, and 2 out of 4 which would have a charge of -1. So the average charge would end up being 0. So most of the molecules are the uncharged HA form, but the concentration, the important thing is the concentrations of cations and anions are equal to each other, which is what I was just describing. So the concentration of H2A plus is equal to the concentration of A minus. So if a pure sample of neutral alanine, where the pKa values are given as such, 2.34 and 9.87, if we dissolve these in water, the A- concentration would be slightly larger than the H2A plus concentration. So it was similar to what we talked about before. So if a pure sample of neutral alanine, pKa1, 2.34, pKa2, 9.87 is dissolved in water, the A- concentration would be slightly larger than H2A plus concentration. So by adding a small amount of acid, some A- would be converted to H2A plus until the concentrations are equal. And this is the isoelectric pH. So this is going to be creating this system where we have equal concentrations between these two. So remember that for our isoelectric point, most of our molecules are in the uncharged HA form, the amphiprotic form. Now, because of the pKa values and the fact that it is dissolved in water, we end up with more A- in solution than we have at H2A plus, which means that in order to convert the A- into H2A plus, we must have an excess of protons. And so we have to add acid in order to increase the concentration of H2A plus. So more protons means that more of them will be taken up by the A- or the HA, which will end up forming more H2A plus. And so eventually we'll get to a point where we have equal concentrations of both. And this will be the isoelectric pH. So the pH here will be equal to halfway between the pKa values. And so it can be used to separate protons from one another. So this is a way of separating protons, because some of their forms, whether it be the neutral forms or the acidic or the basic forms, can change their solubilities. Okay. So one way, this is what I talked about, we would try to get onto today is something called a titration. You may have come across these before in lab classes, where we are reacting a known quantity of acid or base with a known volume of acid or base, but an unknown concentration, in an attempt to try and find the concentration of the unknown volume. So this is a very important thing. It's not just a case of adding hydrochloric acid to sodium hydroxide and seeing how much sodium hydroxide I have, for example, in my flask. That's sometimes what we do in the lab, but really it's training for the workplace environment where maybe we are needing to, I don't know, even something as mundane as producing vinegar for the food and beverage industry. So you need to know what concentration of acetic acid is in your vinegar. And so maybe you're going to do a titration to find that out. It's a very easy way to do concentration determination. Doesn't need any real particularly fancy equipment. Pretty cheap to put together, but very powerful. And it's also used in the cosmetic industries to make sure that the sort of like the pH of the final product is going to be okay, that the concentrations of the different acids and bases don't create a system which may be eventually dangerous to the consumer, because that's something that would be a total disaster if it wasn't suitable for use by your end consumer. That could be very bad. So acid-base titrations. So in an acid-base titration, the concentration of an acid or a base is determined by neutralizing the acid or base with a solution of base or acid of known concentration. So that's a little bit confusing. So you react an acid of unknown concentration with a solution of base of known concentration, or you can do it the other way around. So basically what you're doing is you're doing the neutralization reaction where you're reacting H plus with OH minus to give water. So the equivalence point of the reaction occurs when the number of moles of OH minus added equals the number of moles of H3O plus originally present, or vice versa. So say, for example, I have 0.05 moles of acid in H plus in my solution. my unknown solution, I will need to add base until such times as the concentration of OH minus added, not the total concentration present in the solution, but the amount added is equal to that. So it would have to be 0.05 moles of OH minus added to 0.05 moles of acid, for example. And so the endpoint occurs when the indicator changes color. So the indicator should be selected so that its color change occurs at a pH close to that of the equivalence point. Yeah, so it's not really very good to have a pH color change several pH points away from the actual required concentration. And as we saw in the previous, I think it was buffers part 1, a lot of indicators are based on buffer type systems. So here is kind of an example of a curve for a strong acid, strong base titration. So this is a typical lab experiment. So the curve for a strong acid, strong base titration. So here we have actually all of the values of the added sodium hydroxide and the pHs then that those correspond to. So we have here the volume of sodium hydroxide added to our solution of hydrochloric acid. So we start off at low pH because the predominant species is going to be hydrochloric acid. Then as we add more and more sodium hydroxide, we see initially that there is a limited change in the pH. And that's because at this point, there's still a massive excess of H plus ions in solution. But eventually, the H plus ion concentration starts to decrease. And as we get close and close to the equivalence point, we see that there is a rapid increase in the pH as we move through the equivalence point up into the basic realm where we have an excess of our sodium hydroxide. So conveniently, because these are reacting 1-to-1, we have an equivalence point where, since we're dealing with solutions of the same concentration, so there's 40 milliliters of 0.1 molar HCl, and we're titrating that with 0.1 molar sodium hydroxide, which means that whenever we've got 40 milliliters of both, we will have the equivalence point, which will be pH 7, a totally neutral system where all of the acid has been reacted with the base. And so in solution, all we have is the salt and water. So the overall reaction for this is HCl plus NaOH gives NaCl plus H2O. And so this is going to happen at the equivalence point here. And then if we keep adding base, of course, we will end up in a basic region. Our indicator for this is phenolphthalein, where we see a color change going from this very pale pink to this very vibrant purple. And so at that, as we move through that, we'll see that there is going to be a visual indicator that we have reached the equivalence point. So here are some schematics of what the solution might look like on a molecular scale. So whenever we have the initial system of just the acid, we have hydronium ions totally dissociated in water and the chloride anions. So remember that the HCl is a strong acid, and so we'll totally dissociate in water. Then as we start to add the base, we end up seeing that there is now, in addition to the chloride, there are sodium ions, which came from the sodium hydroxide. There are still hydronium ions, but now some of those hydronium ions have been replaced with just water. Then at the equivalence point, where we have equal moles of added sodium hydroxide and originally present acid, we end up with no acid or base, no hydronium and no hydroxide present in solution. We only end up with water, chloride anions, and sodium cations. And then this is our solution here. We have hydroxide, water, and our different cations, anions. So the initial pH is low. The pH rises very rapidly at the equivalence point, which occurs at pH is equal to 7. The pH increases gradually when excess base has been added. So calculating the pH during a strong acid, strong base titration. So here we have the initial pH, which is where hydronium ion concentration is going to be equal to the HA added. Remember, this is a strong acid, so all of it will dissociate, which means the pH can be calculated as minus log the concentration of H3O plus. So the pH before the equivalence point is really based on the volumes of and the concentration of the different species involved. So pH before the equivalence point, so we have initial moles of hydronium ion is equal to the volume of the acid times the molarity of the acid, or the concentration of the acid. So the moles of OH minus added is equal to the volume of the base added plus the molarity or the concentration of the base solution. So the moles of H3O plus remaining is equal to the moles of H3O plus initially present minus the moles of hydroxide added. So the hydronium ion concentration at some particular point is equal to the moles of H3O plus remaining over the total volume of acid and base in the flask, which means the pH then can be calculated as minus log the hydronium ion concentration. So usually you can get the pH from like a simple pH meter. Maybe it's a benchtop pH meter, or maybe it's a handheld one. Basically, it's not too difficult to get a pH reading, and then that can be translated into the hydronium ion concentration relatively easily. Or if you know the initial HA concentration added, then you can know the H3O plus. Remember, this is for strong acid, strong base, so everything gets dissociated. So pH at the equivalence point. So for a strong acid, strong base titration, the pH at the equivalence point is always going to be 7 because we're just left with neutral water. There's no like weird equilibria going on here. To confuse things a little bit, we're going to end up with pH of 7 at the equivalence point. And so the pH beyond the equivalence point is really just pretty much exactly the same. The difference now is that instead of working with H3O plus, we're now looking at the excess hydroxide present. So obviously, we have to work out the initial moles of H3O plus, then we have to work out the moles of OH minus added. So the moles of OH minus excess is going to be equal to the total moles added minus the moles consumed reacting with our hydronium ion. So remember that in a strong acid, strong base reaction, we have hydronium ion, so H3O plus. So that came from, for example, our hydrochloric acid plus our hydroxide, our OH minus, and those will react to give 2 water molecules. So this will keep happening until one of these is no longer present. So at the equivalence point, the same number of hydronium and the same number of hydroxide have been consumed to give water. But if we keep adding more and more hydroxide, but there is no hydronium, then we just end up with a continuation of continually increasing concentration of OH minus, and therefore an increasing pH. So the moles of OH minus excess is equal to the total moles added of hydroxide minus the moles of hydronium ion initially present. So the concentration then is equal to this. POH then is equal to minus log to the base 10 of the concentration of OH minus, and the pH is equal to 14.00 minus POH. All right, so let's do a sample calculation of this. So 40 milliliters of 0.1 moles per liter HCl is titrated with 0.1 molar NaOH. So this is the same as the titration curve we saw earlier. So the initial pH is simply the pH of the HCl solution. So the hydronium ion concentration is equal to HCl initially present, which is 0.1000 moles per liter. And the pH then is going to be equal to minus log to the base 10 of that concentration, which will give us a value of 1. Now, to calculate the pH after 20 milliliters of NaOH solution has been added, we need to calculate the number of moles that were added and the number of moles initially present of HCl. So the initial moles of H3O plus present is going to be equal to 0.04000 liters, because you remember concentration is always in moles per liter. We were given it in milliliters, so it's our duty to check that we are using the correct units. So we need to convert this to liters. So that's it in liters. So that's how many liters of HCl were present times the number of moles per liter, or the concentration, which is 0.1000 moles per liter. which will give us a number of moles of being 4 times 10 to the minus 3 moles of H3O plus initially present. Now, then we need to calculate the total number of moles of sodium hydroxide which have been added. So the sodium hydroxide dissociates totally into Na plus OH minus ions. Total dissociation happens. So OH minus added is equal to 0.02 liters of sodium hydroxide times 0.1 moles per liter of, as the concentration of that, sorry, is equal to 2 times 10 to the minus 3 moles of OH minus. Now, the OH minus ions react with an equal number of H3O plus ions. So the H3O plus remaining is going to be the initial number of moles of the H3O plus minus the amount of OH minus ions added, because remember, they react 1-to-1. So that will, for every hydroxide that we add, it will react with 1 hydronium, removing it from solution, making water, which means that we'll end up with a remaining concentration, or sorry, a remaining number of moles of hydronium as being 2 times 10 to the minus 3 moles of H3O plus. Then from that, we can get the concentration of H3O plus remaining. So that's going to be 2 times 10 to the minus 3 moles over the total volume of the solution now. So it's no longer just 40 milliliters. It's now 60 milliliters or 0.06 liters, because we have added 20 milliliters of our sodium hydroxide solution. So that gives us a concentration of 0.03333 moles per liter. Put this into our pH calculation. So pH is equal to minus log to the base 10 of the concentration of hydronium ions, which means that the pH is now increased to 1.48 because of this addition of the hydroxide ions from the sodium hydroxide solution. So the equivalence point occurs when the moles of OH minus added is equal to the initial moles of HCl. So when 40 milliliters of NaOH has been added, we'll have reached the equivalence point. So we want to then calculate the pH after 50 milliliters of sodium hydroxide solution has been added. So now, if we say that the equivalence point will have been reached when 40 milliliters of sodium hydroxide has been added, if we add 50 milliliters of sodium hydroxide, we're going to have an excess of hydroxide ions, because all of the hydronium ions will have been reacted with. So the OH minus that is added is going to be equal to the total volume of sodium hydroxide added times the concentration of that sodium hydroxide solution. So that means we're going to end up with a number of moles of hydroxide being equal to 5.000 times 10 to the minus 3. This is the number of moles of hydroxide. Now, to find the excess of hydroxide, we have to subtract from this value the total number of moles of HCl or H plus or hydronium ions present in the initial volume that we were titrating against. So the OH minus excess is equal to 5.000 times 10 to the minus 3 minus 4.000 times 10 to the minus 3, or a value of 1 times 10 to the minus 3 moles of OH minus remaining. So we have 1 times 10 to the minus 3 moles of hydroxide in solution after that titration. So then the concentration of OH minus is going to be equal to 1 times 10 to the minus 3 moles, which will be then over the total volume of the solution. So it's the initial 40 milliliters of our hydroxide, or sorry, of our hydronium from the HCl, plus the added hydroxide will give us a value of 0.01111 moles per liter of our hydroxide ion concentration. So then the POH is going to be equal to minus the log of that concentration, which is 0.0111111 is equal to 1.95. And that will be our POH. Remember, this is not the same as the pH, but POH and pH can be related via their relationship with pKw. So pH is equal to 14 minus 1.95, 1.95 being the POH, which will be equal to 12.05. So that will be our pH of the solution. So you can see the pH has rapidly increased because of the addition of the hydroxide. Okay. I think we'll leave it there for today.